Hello everyone, myself Hemant. I'm here to discuss the first question, first part, which is about converting absolute temperature into IEEE 754 single precision format. The IEEE 754 single precision format consists of 32 bits. The first bit is used to represent psi, and the next 8 bits are used to represent exponent, and the remaining 23 bits are used to represent the mantissa. Here E is the true exponent, but IEEE format has exponent as biased exponent, where biased exponent equal to true exponent plus 127. Here significant means 1 plus mantissa. The given temperature in the question is minus 85.125. Since the given number is negative, the sign bit is 1. Taking the magnitude, the given temperature will be 85.125. To convert this number into binary, we write this number as sum of powers of 2, which is equal to 2 power 6 plus 2 power 4 plus 2 power 2 plus 2 power 0 plus 2 power minus 3. The equivalent binary representation of the given temperature is 101010.001. Taking power of 2 as common, the equivalent binary representation of the given temperature is 101010.101. Taking 2 power 6 as common, we get the significant here is 1.0101010001. So the mantissa is equal to significant minus 1, which is equal to, here 6 is the true exponent and biased exponent equal to 6 plus 127, which is equal to 133, which is represented in binary as 1000101. In a nutshell, the sign bit is 1 as the number is negative, and as we got the bias exponent is 133, which is represented in binary as 100000101, and the mantissa is this, which can also be written as. To convert the given number into hexadecimal format, we divide the number and group every 4 bits and convert them into hexadecimal format. Finally, we get the hexadecimal number as C2AA4000. As we represent hexadecimal number using the prefix 0x, the number is 0xC2AA4000.
My name is Manat Karthik. So let's discuss the second part of the first question. So we need to convert the absolute pressure into IEEE 754 single precision format. So the given pressure is 5/6, which is positive, so the sign bit is 0. Taking the magnitude part 5/6, we can write 5/6 equal to 1/2 plus 1/3, and which can be written in terms of sum of GPs as 1/2 plus 1/4 plus 1/4 whole square dot dot dot. By converting it into equivalent binary representation, we get 0.110101 recursively. So by taking common 2 power minus 1, we can write as 1.1010101010. The mantissa of its equivalent is 101010 recursively. So the true exponent is minus 1. Since the bias exponent equal to 2 exponent plus 127, we get 126. By converting it into binary, we get 0111110. In a nutshell, sign bit equal to 0, biased exponent equal to 0111110, mantissa equal to 101010 recursively. Together we can represent the floating point number as 0011111010 recursively up to 23 bits. Since we need the number in hexadecimal format, group the bits of size 4 and convert it into hexadecimal format. Eventually, pressure coefficient in IEEE 754 format in hexadecimal equal to 0x3F5555555.
Hello guys, I am here to explain second question, which is regarding instruction and coding. I am Vijala Durga Suhas. Here given in the question that the instruction length is 32 bits And given that the number of general registers equal to 256, if we assume the number of bits equal to n which are used to address the registers, we know that 2 power n equal to number of registers, then 2 power n equal to 256. Hence, n equal to 8. Here it is also given that there are 4 types of instructions. The first one is complex, and the second one is simple, and the third one is memory, the fourth one is control. Now I'm going to explain about the complex instructions. Here, given that 32 instructions are required for the complex instruction and needs 3 registers. So we are gonna take the 32 instructions as opcode and 3 registers as operand. We know that 2 power n equal to 32 and n equal to 5. So at least 5 bits are used to express it as opcode. And operand is of 8 into 3 bits, as there are 3 registers and 8 bits are used to express each register. So eventually operand is of 24 bits. Remaining bits equal to 32 minus 5 minus 24, which is 3 bits. So effectively the opcode is of minimum bits used to express it plus remaining bits, which is equal to 5 plus 3, which is 8 bits. So when the opcode is of 8 bits, we take the first 3 as 000 and the next 5 as XXXXX. So the XXXXX is from 00000 to 11111, which is of 32 instructions, and next 24 bits are operand, which are of 8 bit plus 8 bit plus 8 bit, of which is for 3 registers. I'm going to explain simple instructions now. Given it has 16 instructions and 2 registers and 10-bit intermediate value. So we are taking 16 instructions as opcode and 2 registers plus 10-bit intermediate value as operand. So when 2 power n equal to 16, n equal to 4. So at least 4 bits are required to express opcode. And operand is 8 into 2 plus 10 bits, where 2 is for 2 registers and 8 is for 8 bits required to express each register, and 10 is for 10-bit intermediate value. So operand is of 26 bits, and remaining bits equal to 32 minus 4 minus 26, which is equal to 2 bits. So effectively the opcode is of minimum bits required to express opcode plus remaining bits, which is 4 plus 2 bits, which is equal to 6 bits. Now the 6 bits are written as 11xxxx. So XXXX is from 0000 to 1111, which is of 16 instructions, and the operand is of 8 plus 8 plus 10 bits, which is 2 registers plus 10-bit intermediate value. Now I'm going to tell about control instructions. So given it has 64 instructions and needs 1 register and 12-bit intermediate value. So now the 64 instructions are taken as opcode and 1 register plus 12-bit address value is taken as operand. So when 2 power n equal to 64, n equal to 6. So at least 6 bits are required to express opcode. And the operand is of 8 into 1 plus 12 bits, which is 20 bits, where 1 is for register and 8 is for 8 bits to express each register, and 12 is for 12-bit address value. So remaining bits are 32 minus 6 minus 20, which is 6 bits. So effectively the opcode is of minimum bits to express it plus remaining bits, which is 6 plus 6, which is 12 bits. So now the opcode, the 12 bits of opcode is written as 010000 XX XX XX. Now the XX 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 is written as 000000 to 111111, which is of 64 instructions, and the remaining 20 bits are operand, where 8 bit is for register and 12 bit is for 12-bit address value. Now I'm going to tell about memory instructions. Now memory instruction requires 2 registers and 6-bit displacement value, which is taken as operand. Now the operand is 8 into 2 plus 6, where 2 is for 2 registers and 6 is for 6-bit displacement, and 8 is for 8-bit required to express each register. Eventually operand is 22 bits, and remaining bits are 32 minus 22, which is 10 bits. So the opcode is now 10 bits. Now you can see at the below that it is 8 plus 8 plus 6, where the operand is of 22 bits. Now I'm going to tell about its opcode. The opcode is written in many ways, which is 001XX XX XXX. That X part can be written as 000000 to 111111, which is of 128 instructions, and it is also written in 10XX XX XX XX. Now the X part can be written as 00000000 to 111111, which is of 256 instructions as 2 power 8, and it can also be written as 01YYYY and XXXX. Now for the Y part, we have written in the control instruction as 0000 is already included there, we can not write it. So we are starting from 0001 to 1111, so which is of 15 instructions. Whereas for X part it is from 0000 to 1111, which is of 16 instructions. So for this part it is net 15 into 16 instructions, which is of 240 instructions. So the net is of 128 plus 256 plus 240, which is 624 instructions, and the answer of the question.
Thank you for your presence.